Hello all. In this lecture we'll see about properties of relational decompositions. So we'll mainly see about an introduction about this different properties of relational decomposition. Then what do you mean by this dependency preservation? What is lossless join? Then also an algorithm to test whether it is lossless join property, whether that decomposition is satisfying lossless join property, and also when it is binary decomposition, that is if you are decomposing into two relations, we have to check whether it is lossless join or not. So introduction. So we have some basic definitions to understand the thing behind this decomposition and all. So what is meant by this universal relational schema? So it is a relational schema R with a set of attributes A1 to AN that includes all the attributes of the database. So we'll consider the whole attribute set as a universal relation. That is, we have a single relation with all the attributes in the database. This R is known as a universal relation schema. Universal relation schema. Then what do you mean by this decomposition? So we have some functional dependencies on these attributes. So we have some functional dependencies on this universal relational schema on these attributes. So the process of decomposing the universal relation R into a set of relation schemas D equal to R1, R2, etc. Rm. Okay, we will decompose this R into R1, R2, etc. Rm. That will become the relational database schema by using the functional dependencies. So we have a set of functional dependencies and we have this universal relation. So based on that functional dependencies, and we have already studied the normalization procedure and all. So based on that normalization procedures, we will follow those normalization procedures. We will apply the functional dependencies, and using that functional dependencies, we will decompose this universal relation into R1, R2, etc. Rm. So this is known as decomposition. So we have already seen this. So we start from a relation, we will check whether it is in first normal form, second normal form, third normal form, like that we will be checking. If it is not in the particular normal form, we will decompose it. Okay, so we will decompose into R1, R2, etc. Like that, there will be different relations that will be formed. Okay, so if you take the union of all these relations, it should be the total relation schema R. Okay. Then we will see what are the properties of the relation. So this is two definition. This is universal relation, and we can decompose into separate relations R1, R2, etc. Then what are the properties on this decomposition? So when we decompose into R1 and R2, which all properties that should be satisfied? So first one is attribute preservation condition. Attribute preservation. So you know what you mean by this attribute preservation. That is, we have A1, A2, etc. N number of attributes in this relation. And when we decompose into R1 and R2, etc., Rm, all these n attributes should appear in some relation. We should not lose any of these attributes. Then it is known as attribute preservation condition. Okay, so each attribute in R, that is in the relation schema, will appear in at least one relation schema Ri in the decomposition, so that no attributes are lost. This is known as attribute preservation condition. Okay, all the attributes should be preserved even after decomposition. So this is a condition. This is another thing. Each individual relation Ri in the decomposition D should be in BCNF or 3NF. So we should try to normalize each relation. So when we decompose all the relations R1, R2, etc., then that individual relation R1, R2, etc. should be in BCNF or at least in third normal form. Okay, so that's another property. Then, when we decompose into BCNF or third normal form, we should not generate spurious tuples. So we have already seen this, what is spurious tuples and all. So it should be prevented. There should not be any spurious tuples. Okay, that is unwanted tuples. When we join, perform natural join, unwanted tuples will come. So that should not be there. We'll see what is the spurious tuples in the later session. Then another property that should be satisfied is it should be all the dependencies should be preserved. All the functional dependencies should be preserved. That is, in R, the universal relation schema, there are some functional dependencies. So all those functional dependencies should be preserved in any of the decomposition. If if there is a functional dependency A to B, it should appear in any of R1, R2, etc. So that is known as dependency preservation property. So one is attribute preservation property. Then we should prevent from generating spurious tuples, and also dependency preservation should be there. Of the three conditions, of the three major conditions, attribute preservation should be there. None of the attributes should be lost. Then prevent from there should not be any spurious tuples should not be generated. And in the case of dependency preservation, in certain cases we have to avoid this. So in some cases dependencies may not be preserved. Okay, when we normalize to BCNF, this dependency preservation property will be lost in some of the cases. Okay, so we'll see what is this. So attribute preservation you understood. Now second is generating spurious tuples. So we have already seen this. What do you mean by spurious tuples? So we have two relations, M locations and M project. Now, if we try to perform natural join on these two relations, so in certain cases, when we want to retrieve some information from these two tables, we may have to join these two tables. Then only we could retrieve some information. Okay. So in that case, so if I want to find out how many hours Smith John B worked for a particular project, so Smith John is in this table, and the number of hours worked is in this table. So we have to join these two tables, then only we'll get the result. So when we perform this natural join on these tables, so it will be something like this. So this is natural join to the tuples in M project 1 and M locations just for employee SSN equal to 1, 2, 3. Just for this employee, if we perform this natural join, we could see there are many spurious tuples that are generated. This starred one. So all these are formed due to natural join. So all these are spurious tuples. Spurious tuples means this is actually conveying unwanted information. So actually 1, 2, 3, 4, 5, 6, 7 SSN is for Smith John B. But you could see in this row, in this tuple itself, 1, 2, 3, 4, 5, 6, 7 is mapped to English Joyce. Okay, that is wrong. 1, 2, 3 again it is mapped to English Joyce. Again in this row also 1, 2, 3, 5 is mapped to some other employee. So actually SSN belongs to a single employee, that is unique. But when we perform this natural join on these two tables, what happens is there are many spurious tuples that are generated like this. All these are spurious tuples. These are unwanted information and wrong information. Actually they are conveying wrong information. So such kind of spurious tuples should not be generated when we decompose. So this happened because when we have decomposed into these two relations, and this does not satisfy that property, that is lossless join property. So we have already seen what is lossless join and lossy join. So these tables, this decomposition is not satisfying lossless join property. Okay. Then, so that is about lossless join property. Then we have dependency preservation property. So what do you mean by this dependency? So hope you have understood what is attribute preservation and what is meant by how to prevent, what do you mean by this preventing this spurious tuples. So actually this is for lossless join property. In other words, we can say that this decomposition should satisfy lossless join property. Then the third property is dependency preservation property. So before going into the dependency preservation property, we should have some definitions. So first one is what do you mean by this decomposition? Okay, decomposition. Sorry, what do you mean by this projection? So projection. So if we have a set of dependencies F on R, so F is a set of functional dependencies on the universal schema R, the projection of F on Ri on a particular decomposed relation R1 or R2 or anything, it will be denoted by pi of Ri of F. Okay, so this is denotes the projection of F on Ri denoted by pi of Ri of F. Then and this Ri is a subset of R. So this is universal relation and it will be a subset of this R. Then it is the subset. So projection will be the set of dependencies x to y in F closure, and it should be there in F closure. So you have already learned what is this functional dependency closure. So if we have a set of functional dependencies F on R, if the projection of F on Ri, the F on Ri denoted by this, and Ri is a subset of R, it is a set of functional dependencies. So projection means it is a set of dependencies x to y in F closure such that the attributes in x union y are all contained in Ri. So if you have a function in the Ri, in the relation Ri, for example, if it is relation R1, in that relation R1, there will be some functional dependency x to y. That x to y should be in F closure. Okay, that's the meaning. So that x to y should be there in F closure. F closure is a closure of this universal relation. Then it is known as projection of F on Ri. So what do you mean by dependency preservation property of a decomposition? So a decomposition D equal to, if you are decomposing into R1 to R1 of R is a universal relation, it is dependency preservation with respect to F if the union of all the projections of F on each Ri in D is equivalent to F. Or in other words, we can say that projection of R1 of F, union projection of R2 of F, etc. All this taking the closure equal to F closure. So this is the meaning. So then we can say it is dependency preservation. So you should understand projection first. So projection means it is a set of functional dependencies x to y in F closure, and these attributes x and y are in Ri. Okay. So if you decompose like this, then it is dependency preservation if F is a functional dependency on R, we have this F closure. That is all the set of functional dependencies that can be derived from this F. Then we have some projections. The R1 we have some functional dependencies, R2 we have some functional dependencies, Rm we have some functional dependencies. What you have to take, we have to take the union of all those functional dependencies. That is what we have taken. So union of all those functional dependencies, and it will be a huge set. And if we take the closure of that F closure of that set, then it will be equivalent to F plus. Then we can say that it satisfies that dependency preservation property. So we'll see an example of this dependency preservation example. So we have already seen this example. So we have seen when we studied the third normal form and all. So there's lots 1 and lots 2 relation. So after decomposition, we'll get lots 1 and lots 2. Now if we see this, there is a functional dependency area to price. So here area to price, it is in second normal form, but it is not in third normal form, because area to price, area is not a super key and price is not a prime attribute. So we have to decompose this into two relations, so lots 1a and lots 1b. So now these two relations are in third normal form and all the dependencies are preserved. So if you see fd1 and fd2, fd1 and fd2 are in this relation, and fd4, this is in this relation. So it is known as dependency preservation property. Then this is an example for non-dependency preservation property. Here if we take lots 1a, so if we take this lots 1a, so we have already studied this lots 1a, there is, if we try to normalize into BCNF, so there is a functional dependency area to county name. So it is in third normal form, but area to county name area is not a super key. Okay, but county name is a thing. A county name is a prime attribute, so it is in third normal form. But area to price, area is not a super key, so it is not in BCNF. So if we try to normalize this, what happens is we will decompose this relation into these two. So we will get property ID, area, lot number in a relation, and lots 1A we have area and county name. So we have removed this functional dependency and kept it in a separate table. Okay, so now both these tables are BCNF. So if we check, the super key is property ID and area and lot number depends on property ID. And similarly here county name depends on area, where area is a super key. So these two relations satisfy third normal form. Oh, sorry, BCNF. Now if we see these two relations, this decomposition, we can see this FD2. FD2 means property ID is dependent on county name and lot number. Similarly, area is dependent on county name and lot number. So that FD2 is lost because we have separated county name in a different table. So we have separated county name in a different table. So we can see this county name and lot number, that functional dependency. FD2 is lost when we decompose. So this is known as non-dependency preservation, non-dependency preserving decomposition. Another example, we have already seen teach relation. So this is the teach relation, and we have already seen the functional dependencies are these two are the functional dependencies. So if we try to decompose into BCNF, we will get we can either do like R1 and R2 like this, or R1 and R2 like this, or R1 and R2 like this. So we have already seen this example when we learn BCNF. So all these are BCNF, in BCNF. But if we take in all these relations, some of the this student comma course to instructor, that functional dependency is lost in all these relations, in all these decomposition, because student and course are in two different tables in all these relations. So what happens is this functional dependency FD1 is lost in all these decomposition. Okay. So, dependency preservation property of a decomposition, there is a claim. So, it is always possible to find a dependency preservation decomposition D with respect to F such that each relation Ri in D is in 3NF. That is, we can always normalize to third normal form satisfying this dependency preservation decomposition. Okay, it is always possible. It is always possible to decompose into third normal form satisfying this dependency preservation property. But when we try to normalize to BCNF, we cannot guarantee that dependency preservation property. Okay. Then non-additive lossless join property. So what is this non-additive lossless join property? We will define that thing. So first we have seen attribute preservation, second we have seen dependency preservation, third property is non-additive lossless join property of a decomposition. So this is the definition of that non-additive or lossless join property. A decomposition D equal to R1 F2, we are decomposing into R of R, has a lossless non-join property with respect to the functional dependency F on R if for every relation state R of R, at every state that satisfies F, this condition should be hold, that where star denotes the natural join of all the relations. So if we perform natural join on all the relation state, so we have already seen M projects plus M, when we perform natural join, that should be R itself. So whenever there is a relation state R of R, R of R, and when we decompose that R of R into 2 or 3 tables, and again when we perform this natural join, when we try to join all these relations, it should be the initial R itself. So hope you have understood this. So we have an initial state here, R of R. Okay, this small r represents the initial state of this universal relation. Then what we do is we decompose that relation into R1 and R2. Then after that again if we join R1 and R2, this is actually joining, natural join. When we perform R1 and R2 natural join, we should get the initial R itself, small, that is the initial state itself. Whatever data that was there, that should be there. No new data should be added to that. So that is why it is known as non-additive joint property or lossless joint property. Okay. So when we perform join, so when we after decomposition, again we try to join these two tables, we should get the first table itself. So that is a basic thing in non-additive or lossless joint property. So there is an algorithm to test whether it is the decomposition satisfies lossless joint property or not. So this is an important thing because you may be asked question based on that. You will be given some decomposed relations, and you have to find out whether it satisfies lossless joint property or not. So it is an easy algorithm. Okay, it is very easy. So you have to understand how to do this. So you have a universal relation R, and you have decomposed D into R1 and R2. So this is the input that is given, and you know the set of functional dependencies. So you will get the decomposed relations R1, R2, etc. And also you will be given the F as set of functional dependency. So this is this is the algorithm. So before going into this algorithm, we will start with an example, then you will understand. Okay. So example is this one. So we have a universal relation R. Okay, R, SSN, these are the attributes of that universal relation. And we have two decomposition, M locations and M project 1. So we have already seen this example, E name and P location. M project 1 is SSN, P number hours. And we have, this is the input that is there. The functional dependencies also we know. Now we have to check whether when R is decomposed into R1 and R2, this R1 and R2 is having a lossless joint property or not. So we have already seen this example, M location and M project. This does not, it's not satisfying this lossless joint property. Okay, it is not non-additive joint property. It is not satisfying that property. So how to check with this algorithm? So first step in this algorithm is create an initial matrix S. We call it as an initial matrix S with one row I for each relation Ri. So if we have two decomposition, we have to we will have two rows R1 and R2 and one column for each attribute Aj in R. So there should be, if there are n number of attributes in R, so we have to make n number of attributes in the table. So this is the thing. The first step what you have to do is, if we have two decomposition, we have to have two different rows. If we have three R1, R2, R3, then there will be three rows. Then the column name should be the attributes of the universal relation, that is SSN, E name, P number, P name, P location, hours. Okay. So that's the first step in the algorithm. Then in the second step, what you have to do, set. So we have to input some values. So we have to set some values of Sij. So Sij equal to Bij for all matrix entries. So you have to simply put Bij values. That is, so the first will be B11, B12, B13 like that, B16. Then second row will be Bij. So it should be Bij. So I denotes this R and J denotes this column value. So B21, B22, B23 like that we will be setting. Okay, this is the second step of the algorithm. Now third step, what you have to do is for each row, so we have to take each row representing relation schema R1. Then for each column, from after taking each row, then we have to take each column representing Aj. Then if the relation Ri includes that attribute, that particular attribute, then we have to change this Bij value to Aj value. So if that attribute is present in the decomposition, we have to set that Aj, Sij to Aj value. So Aj will be a unique symbol. So if you see this, now in the second step, what you have to do is, we have to check each row. So we have to check R1, and in this R1 we have to take each column, and you have to check whether, what you have to do is, in R1 we have E name and P location. So these two attributes are present in R1. So what you have to do is, under E name, in ename we have to change this b12 to aj value. That is, we have to change it to a2. So we have to change this b1 to aj value. Aj means a2. Then P location is present in R1. So in R1, P location it is B15. So we have to make it as A5. That is what we have done here. In the second relation, we have SSN. So SSN should be set to AJ value. So that is should be A1. Then we have P number. P number is B23. We have to make it as AJ. AJ is A3. Similarly, we have P number. Then we have hours. Hours we have to set this as A6. So we have changed it to A6. Then similarly hours, after that P name we have to change A4, A5, like that we have to change. So the next step we have to make it as AJ values. Okay, that is what we have done here. Okay, hope you have understood this. Then so the third step is also over. We have changed to AJ values. So if that attribute is present in particular decomposition Ri, then we make it as AJ. Now the fourth step, again we have to repeat the following loop until complete loop execution results in no changes in S. So what we have to do is, we have to, for each functional dependency x to y in f, so we have to take each functional dependency. So after that only we will be taking each functional dependency. So for all rows in S that have the same symbols in the columns corresponding to X part. So if we have same symbols in X, then we have to change the symbols of Y. So we will see what is this step. Then you will come to that algorithm. Otherwise it will be difficult. So what you have to do is, now we have set, this is after completion of third step. Now we have to take each functional dependency. So we have to take SSN to ename first. Now SSN to ename. So what you have to do is, SSN part we have to check the column values. We have to check whether we have same symbols in the column values. So here SSN to ename, both these are having different values, B11 and A1. So we should not do anything. Then next we have P number to P name and location. So we have to take P number, that is the X part. So P number, we have B13 and A3. So those two are having different symbols. So we can remove, we should not do anything there. Then we have to take SSN comma P number to ours. So we have to take the combination of SSN and P number. So here itself we can see that it is different. So we should not go for this P number to this thing. So we should not do anything there also. So if we have the same X part, if we have the same symbols in the X part, then only we have to do something here. So if there is, for all rows S that have same symbols in the columns corresponding to the attributes in X part, then only we have to do all these things. So otherwise we can go to the next step. So if a row is made up of entirely, so we'll see this in the second example. Okay, so if a row is made up of entirely of A symbols, then the decomposition has a non-additive join property. Otherwise it is not. So if we see this example, so after completion of that step, none of the x2 y x is same. So this table remains as such. So what you have to check is if any of the rows have complete A symbols alone. So if we see all these, we have B symbols also in this row, and also in this row we also have one B symbol. So then it does not satisfy this lossless join property. So that is algorithm. So we have already seen this. This decomposition does not satisfy this lossless join property. Okay, so we will see the third example as the next example. Then you will understand what is that next step. One step we have missed. We didn't do this step. Okay, what is happening inside this whole paragraph? That can be seen in the next example. Okay. So in this example, we have SSN2. So this is a decomposition, SSN project, and we have decomposed into three relations. So we have R1, R2, R3. So this is a universal relation with all the attributes, and this is a decomposition R1, R2, R3. Okay, and M has SSN ename, all these. Then this is a functional dependencies, set of functional dependencies F. So this is the input. Okay. Now we have to check whether this decomposition is satisfying lossless join property or not. So first step is we will have three rows because we have three decompositions, so we have three rows R1, R2, R3. Then after that, what you have to do, we have to give all the attributes. All the attributes will be represented in the column. So that is what is done. SSN, E name, P number, P name, P location, hours. Then after that, each column or each value should be replaced with Bij value. So that is what it is done. B11, B12, B13, B14, like that we are doing. B21, like that. Then B31, B up to B36. Okay, so we have set the symbols. Then the next third step, what we have to do, so we have to take each row. We have to take R1 and we have to check whether which all attributes are there in R1. So we have SSN and E name. So what we have to do, B11 should be replaced by AJ value. So it should be made AJ. Okay, AJ. So that is what we have done here. We have made it as A1. Then E name is also present. So it should be also made A2. So if we see A1 and we have changed A2. So those are the only two changes in the first row. Okay. Then in the second row R2 we have P number, P name and P location. So P number, P name and P location should be changed to A3, A4, A5. So we have changed it to A3, A4, A5. Then works on it is R3. So we have SSN, P number and hours. So SSN should be changed to A1. Then this should be changed to A3 and hours it should be changed to A6. So that is what we have done here. It has been changed to A1, A3 and A6. Okay. So that is the completion of third step. Now the next step is we have to take each functional dependency. So you have to take each functional dependency. So till now we are taking only attributes. Next what you have to do is we have to take the first functional dependency SSN to E name. So the fourth step, so that's the algorithm. So we have to take each functional dependency x to y in f. Okay, so we have to check whether we have same symbols in the x part. Okay. So if we take this example, what we have to do is we have to check whether we have to take the first functional dependency SSN to E name, SSN to E name. So SSN, we have to take the x part, that is the x part. So you have to check that column, SSN column. We have to check whether there is we have the same symbol in in the SSN column. So we can see this here A1 and A1 both are same. So here SSN R1 row is having A1 and R3 is also having SS1. So if there is same symbol, then we have to do one thing. So if we have same symbol, now in the E name part, so Y part is E name. So in the E name part, we have to check such kind the E name part also. So if we check here, we have A2 here and we have B32. So if there is an A part, if the X part is same, we have to check the Y part, and in the Y part, if they have A symbol, then make the other one also the same A symbol. That is, we have to change this B32 to A2. So we have to change that B32 to A2. That is SSN to E name. If we have the same SSN value, then we have to change the Y part also. When we change that Y part, if that Y part contains an A value, make the other one also the same A value. That is A2 should be this B32 should be made A2. That is what we have done here. Okay. Then we have to take the next functional dependency P number to P name and P location. P number to P name and location. So P number. So this is the X part. P number is the X part. Now we can see that R2 and R3 are having the same A3 value. Now what we have to do is we have Y part. So Y part is P name and P location. P name and P location. So what we have to do is we have to check the Y part. now y part we have a4 and a5. So what we have to do is we have to change this b values to the a values. So we have to change this to a4 and a5, the same a4 and a5 also. Okay. So that is the next part. Then after that, we have to check SSN comma P number to ours. So we have to check this row again, SSN comma P number. So that combination should have the same value. So if you check this A1 comma B13, here it is different, and here also it is different. So there is no X part is not same in any of the relations. So we can stop that algorithm there. Now what you have to check the last step. So we have to check whether any rows contain complete A values only. So if we check R1, so R1 row, we have B values also. In the R2 also we have B values. But R3 we have complete A values only. We have A1, A2, A3, A4, A5, 6. So if we have only A values, then this decomposition is satisfying lossless join property. So that is the algorithm. Now we will come back to the algorithm. So I hope you have understood till here. You have made this A values. Then after that, what you have to do? So we have to take each functional dependency in X. If we have same symbols in X, make the symbols in each column that correspond to the attribute in Y be the same in all these rows as follows. We have to make the Y symbol also same. So if any of the rows has an A symbol for the column, set the other rows to the same A symbol in the column. So if it is in the Y column, if you have no A symbol exists for the attribute in any of the rows, choose any one of the B symbol and that appears in one of the rows for the attribute and set the other rows to the same B symbol. So if in the Y part, if A symbol is not there, then make it into any of the B symbol. So if the Y part is having B13 and the next row is having B23, you can either set to B13 or B23. Both those B parts should be same, that's all. So we have seen this thing. So if a row is made up of entirely of A symbols, then the decomposition has a non-additive join property. Otherwise, it does not. So in this first example, we can see that it does not contain complete A values. But in the second example, after performing all these steps, we can see all these having the same A symbols. Okay. So one more thing you have to note is the second thing. In the fourth part, one more thing you have to see, if no A symbol, if in the Y part, if any of the rows has an A symbol for the column, we can make it in the same A symbol that we have seen in the example. If in the Y part, no A symbol is there, if no A symbol exists for the attribute in any of the rows, choose one of the B symbols that appears in one of the rows for the attribute and set the other rows to the same B symbol. So if we have two rows and the Y part is B13 and B23, you set it to any value. You can set it to either B13 or B23. If you are making B13, you have to set the other row also B13. If you are going to set the first row as B23, then the other will be B23. Okay. So that you have not seen this example, it may sometimes come in some other example. Okay. So that's what we have seen. If it is complete single row, if any of the rows has complete A values, then this satisfies that non-additive join property. Okay. So then for binary decomposition test, we can have another easy method to test whether it is not satisfying that non-additive join property. So if it is binary decomposition, means we are decomposing into two relations. That is, we have a universal relation R and we are just decomposing into R1 and R2. We can simply test whether it satisfies lossless join property or not. So a decomposition D R1 to R2 of R has lossless join property with respect to the functional dependency F if and only if either any of these conditions should satisfy. That is, the functional dependency R1 intersection R2, that is, there will be some common attribute in R1 and R2, that R1 intersection R2 to that functional dependency to this R1 minus R2 should be there in F closure, or this functional dependency R1 to R2 intersection R2 to R2 minus R1, this difference is in F closure. So if if any of these conditions is satisfied, then we can say that this satisfies this non-additive join property. So we'll see this example. In this, we have already seen this example. So these are the two functional dependencies, fd1, fd2. Now we have to, this is actually, we are decomposing this relation, this teach relation into R1 and R2. This is binary decomposition. Now what we have to do is, we have to check R1 intersection R2. R1 intersection R2 is student. Okay, R1 intersection R2 is student, and R1 in the y part it is R1 minus R2. R1 minus R2 we will get as instructor. Okay, so we will get a functional dependency as student to instructor. So student to instructor is not there in this relation. So that means it does not satisfy that non-additive join property. Or R2 minus R1 can also be done in that case. So student R1 intersection R2 is student. Okay, then R2 minus R1. R2 minus R1 is, if you say, take the difference R2 minus R1, it is student, you will get course. So student to course. So that student to course is not there in these two functional dependencies. So this does not satisfy lossless join property. Similarly, you can check whether this decomposition satisfies lossless join property. So what you have to take, again in this relation also, you have to check the intersection of R1 intersection R2, you'll get it as course. Okay, R1 intersection R2 is course. Then R1 difference R2. R1 difference R2, it is instructor. So course to instructor. Course to instructor, that functional dependency is not there. Then if you take R1 intersection R2 course and R2 minus R1, you will get it as student. So the functional dependency is course to student. So course to student also is not there in this F. So that means it is also not dependency preserving. So you have to simply check this condition. If we decompose into R1 and R2, you have to check this condition, whether this functional dependency is there in the F, in the initial set of functional dependency, or F closure. If that is there, then it satisfies lossless join property. Okay, you can check for this example also. So this is a reference. Thank you.